All right, so it takes me about 10 minutes to set up everything. You know, power supply, the speaker mic, um, the splitter. Now I can actually see what is projected on the monitor right next to me, so that's nice. And then have a OBS, started streaming on the YouTube end. Um, yeah, and my reading glasses. So now we got everything ready. And the time is close, not quite yet. Okay, so all right. All right, excellent. So let me just kind of ask you, about something. You don't have to answer. Um, there are quite a few professors considering teaching classes in what we call a sync flex mode. So if you or high flex, either way. So basically, it allows people to participate both in person, like what you guys are doing here, as well as people who want to participate online. No, it is not an option, not yet. Um, I think the district and the union are trying to work out something so that it becomes a reality for professors who can handle both at the same time. For computer science classes, I don't think it's going to be too big of a deal, for me to look at you guys, see if you guys have any questions, and then keep an eye on either Zoom or Discord to see if something pops up over there. Because I used to teach, synchronous classes, and I just keep an eye on, Discord while I'm teaching. So it's not really that much of a change, so that I have to look at both all of you and also look at Discord at the same time. But if you're in speech or communication or some other classes, that can be a little bit more challenging. So I can understand why some faculty members, some of my colleagues, are feeling um, a little bit. They're more reserved. Okay, they're not. They don't think they're quite ready to take on this modality. But in computer science, I think some of the classes like this one, can be taught that way, which is not to negate what I think is important about in-person classes, where you guys are here, you can ask questions, and it's relatively distraction-free compared to when you're home and you have your pets running around and stuff like that. So there's that. All right. So what you're seeing here, on the projector, that is Joplin, Joplin, which is, last semester or the one before last, I recommended this as a note-taking tool. So if you prefer to type instead of your handwriting your notes on a piece of paper, this app is pretty useful because you can enter your equations in math. And you can see, on the left-hand side is Markdown, which is basically just plain text, typing. And then on the right-hand side is the rendering of Markdown. So you can see, how things can be entered. So I just kind of use this, to showcase, how you can take notes in class if you prefer to use like a tool to help you. Obviously, it is just an option, just one way of taking notes in class, not the only way. If you use OneNote, hey, that's good too. This is just one more alternative to get things done. So you can see how I have typed something here already of note taking in class. I hope you guys are all taking notes. For those people who have exposure to set notations, from high school or some of your other classes, hey, maybe there's nothing that you need to take down your last semester. I mean, last week. Um, but I think it's still a great idea to keep an eye on, what material is new to you, and then take notes. Reviewing of past material in this class is pretty easy because it's recorded. So you can just kind of go back to the recording on last Wednesday kind of fast forward through the stuff that is boring, stuff that you know already. Maybe just go watch the end of the entire lecture, just the last 5 minutes. That will give you the context of where we are now at this point. It's also useful to read ahead. So I haven't really talked about union, intersection, and stuff like that, but that's what we'll be talking about today. So just reading ahead of the class or ahead of the lecture can be very helpful. And then when you have time, it's a good idea to reorganize your notes. In other words, you can put all the definitions at one place. You can put all your explanations in another place. It makes it easier to find the material because the way I organize the material makes sense to me, but it may not make sense to you. So you can reorganize the content to the point where it makes sense to you, and then you can quickly find the material in an exam. All right, so just a quick rundown of what we have introduced so far. We talked about logical operators and the various ways to express the same thing. So the wedge, is the and operator. This is the or. This is logical not. This is implication. And this is if and only if. I'm not going to go through the truth table because we talked about that already, and it is also in the module. So what is left for you guys to do is to make sure that you can find those truth tables really quickly, or if you have everything memorized already, then it's not a big deal. We started on set notations last Wednesday. We talked about the in operator, which looks like this symbol here. So all that means is whether something is in a set or not. It is a Boolean operator. Well, okay, I shouldn't say that. It is an operator that returns a Boolean value. Either something is in a set or it is not in a set. So that is really important as a concept. We also know that when we list items in a set, we use the curly braces as the delimiters. And then the ordering is not important when you are enumerating what is in a set. The last thing that we talked about on Wednesday was the notation of well, what if I want to express membership in a set where the number of items in a set is infinite? There's no way for me to enumerate everything in the set. So we use this notation. Set S is your open curly brace. It includes items X such that P of X is true. Okay, that's kind of what it means. But what this notation is trying to express is exactly the same as as the other notation. It's just that one is more commonly used and the other one is less. So the other form, which I think is actually a better representation, is P of X. P is basically a predicate. You can look at it as a function that returns a Boolean value of true or false. Okay, so P of X is true if and only if X is in S. So in here, if and only if is super important because if I only use if, that is not right. If I use only if, it's also not right. You have to use if and only if. And I believe the last topic on Wednesday was how the if keyword in programming really should have been if and only if. And I believe that kind of sums up everything. It's amazing to myself that I could remember what I talked about in 4 days, 4 days ago, because there are times when people ask me, Tech, could you just repeat the last sentence? I go like, no, not because I don't want to, but because I really cannot remember. So that's I just find that to be a little bit interesting. All right, so we are continuing. So I'm going to use this as a way for me to introduce examples and whatnot, kind of in an impromptu way. Markdown is really great in some other things. You can consider using this in your programming classes as well, because you can actually insert code. Like if I want to insert like a block of C code, this is how I can do it. And if I do this, okay, let's just say we say int +1. Okay, so +1, which takes int x as a parameter, and I just say return x +1. Okay, so totally trivial example, but you can see how it's rendered on the other side. It is syntax highlighted already. So if you're taking CISP 430, 400, This can potentially be useful. I mean, it's not really going to be helping this class much, but when you move on to a 4-year university, this can be a tool that you can use to take notes. Okay, it's just another option. All right, so what we'll do today is continue the discussion of notations in using set. So this is where you can download a Joplin. It's joplinapp.org, and you can download it and have it installed in Windows, Mac OS, Linux, as well as the mobile platforms. I do not recommend the ones for the mobile platforms um, because there are reasons why I cannot remember, but it's not as good as the ones for the desktops. So that's one thing. I'm going to close that tab, and we're going to move on to the content of this class. Are there any questions at this point? Anything you guys might need to bring up? All right. And we talked about how to evaluate whether two sets are the same. Basically, if you have set A and set B, if everything is A can also be found in B and vice versa, then the two sets can be considered equivalent. That kind of makes sense. We talked about element of, okay, and we talk about whether a set can be an element of another set, and the answer is yes. Okay, you can definitely have a set being a member of another set. And then we talked about, this is the last topic, which is a set with an infinite number of elements, and hence the notation that I just described earlier that was in the notes as well. For those of you who want to use Joplin or something like that, and you want to find out, how what is behind the scenes, like the LaTeX notation, you can always just right-click on something here, show math as, and then go to text command, and that will show you exactly what I used, how I typed in the math notations. It can come in handy, even though it's not required. All right, so section 6, talks about a set with no elements. It is also known as the empty set. So the empty set has several notations. Mathematicians like to use something that looks like phi. But in this class, I really just like to know the notation open and close curly brace because it really makes sense that there's nothing in this particular set. We good? Okay. And now we talk about set operators. So what I would usually do in this case is I will show you, what it looks like, and then I will go through a few examples. The first one is intersection. This is the intersection operator. It requires both sides to be sets, and then it returns a new set. Okay. So now the question is, what about this new set? What is so special about it? So A intersecting with B will give you a set. So you can see the curly notation, the curly brace notation, where each element in the intersection of A and B has to satisfy this requirement, which is E can be found in A and E has to be found in B. Or the better way to say this is E is in the intersection of A and B if and only if E is in A and E is in B. Is that notation okay? Does everybody understand what is intersection of two sets? We good? All right, cool. So I am going to give you some, kind of exercises. Okay, so the first thing is, and this is what I type, to start a bullet in a bulleted list. It's just an asterisk space. And let me ask you about this. We have an empty set, and to use the intersection is called a cap. Okay, so backslash cap will give you the intersection symbol, and we'll just have 1, 2, 3 here, and I want to find out what is the answer to that expression. Let me see if I can zoom up a little, scroll up a little bit so you guys can see in the back. So now the question is, what is the answer? What does this equal to? So once again, we're using the intersection operator. It has two sets. One, yep, go ahead. The empty set itself, very good. So the answer to this question is just the empty set. Because whatever is the same as the intersection between these two, every element in this particular set has to be found in both of the sets over here. But in this case, because we have an empty set, by its very definition, the empty set has nothing. Nothing belongs in the empty set. So as a result, you cannot have anything in the resulting intersection. Yep.
So, what order would the elements of the resulting set be if they weren't sorted in any way?
You can use any ordering. Okay, you can use any ordering because because in this class we are only using the more traditional definition of a set notation. So there's no inherent ordering to elements in a set. You can enumerate your membership in any way you want. So there's no specific order that you need to use. All right, so this is a tricky one. Let us go back to some of the more easy concepts. So we can have 1, 2, 3 in one set, and then we do the intersection with 2, 3, 4. This one is easier, and it's better as an illustration. So what should be the answer in this case? We have 1, 2, 3 as a set, 2, 3, 4 as another set. What is the intersection between these two? Go ahead.
A set with 2 and 3?
Yep, just 2 and 3. That's right. Okay, so we have 2, 3 in the intersection itself. Very good. Any other questions? Any questions about this? Yep.
What if 2 and 3 in the second set were rearranged? 3, 2, 4.
Doesn't matter. You can. Okay, so it would still be the same answer no matter how you order things inside a set, because the ordering within a set does not matter.
So would 3, 2 also be acceptable answer?
Yeah, absolutely. Yep. 3, 2 is just as good, and you can list these things in any order if you want. I mean, it doesn't really matter. Because the only question you can ask is this thing in a set? You cannot ask what is the position of this in a set. And since you cannot ask the question of what is the position of this thing in a set, the ordering becomes insignificant. Yep. All right, so are we good so far? All right. Let me give you another one. Okay. And this one does relate to the concept of empty set as well. Okay, so let's go ahead and take a look at this one. All right. Okay, first question is that even okay? Can we have an empty set in a set? The answer is, I don't see why not. It's just basically you have a bag that has nothing in it, and that bag is inside another bag. I mean, you can have it physically, so I cannot understand why it cannot happen, when they are symbolic. But the question now is, what is the actual answer to this question? Which is basically a tricky way to ask, is a set containing an empty set, is that outer set empty or not? So what would be the answer here? Just the, okay, so I just want to be sure, is that what you're proposing? The answer is the empty set? Well, the answer is no. We need another, which means the answer is not an empty set. It is a set that contains empty set as its element. All right? Because you can have a bag and it contains another bag, right? But the bag, the inner bag can be empty. But the outer bag is not empty because it does contain a bag that turns out to have nothing in it. Right? So you can draw a picture. Okay, I would recommend if you are visual or if you like to use analogy to understand abstract concepts, this is what I would draw. Okay, you have a bag. Inside there's another bag, but this inner bag is empty. So from the outer bag's perspective, it is not empty. It has an empty bag inside of it. It's just like you can create a folder, and then you create another folder within this folder, and the inner folder is empty. You can have that to happen as well. So, so this is the sort of thing that you might want to take notes of in the class. Would not be whatever is on the projector because that's already being recorded and streamed to YouTube as we speak. Yep, go ahead.
So a set contains itself?
A set cannot contain itself. There's no notation to do that either. But a set cannot contain itself. That's a good question, but it cannot.
Wasn't there like a really historically important like mathematical proof regarding that question?
I
Like,
have
proved
not.
that math was not solvable or something like that.
I have not checked out the argument in mathematical terms, but I just know that a set cannot contain itself. Yep. All right, very good. So now we are moving on to union. So union is defined down here, and you can see A union B, or the union between A and B, will consist of elements such that the element is a member of A or the element is a member of B. Once again, the word or the phrase "such that" is somewhat ambiguous. I personally prefer to look at it using the other way. So now I did not give you the other definition, so I'm going to give you the other definition in here, just so that we have a way to kind of correlate the two. So this one is saying, okay, let me go back to the page here. So A union B is that. Okay, so that means the same thing as E is in A, union is cup. Okay, if one is cap, the other one is cup. So an element is in the union of A and B. I'm going to put these in parentheses and use one more level of parentheses, so this way there's no confusion whatsoever. So this, and then if and only if is left, right arrow with an uppercase L. If and only if in parentheses again. So okay, this way is better because you can actually see how the equation is constructed, just gradually. So now we have this thing, and then or this thing here. And what is in here is E is in A, or E is in B. So for the most part, you guys can just focus on the right-hand side, because otherwise you'll be just reading what I'm typing. But if you're learning how to enter the equations, then you're also looking on the left-hand side, maybe when you're reviewing the video, can be helpful. So that's how union is. That's another way to define union, is an element is in the union of A and B if and only if the element, whatever element we're talking about, is in A or it is in B. It doesn't have to be in both. It has to be in one of them, at least one of them. It can be in both, but it has to be, in one of them. So to use our earlier examples, okay, I'm just being super lazy here. And I don't think Joplin has search and replace, which Vim has, okay, which is handy to have too. But we can still do it like this, change all the caps to cup, and then we'll try to figure out the answers to all of those questions. So this is what I want you guys to do when you are studying and when you're reading ahead of time, is to give yourself examples to try out, okay? Now, obviously, when you are learning the material, sometimes you may not know what the proper answer is supposed to be. Sometimes it's not obvious. Well, maybe it is this or maybe it's that. In that situation, you can send it to me. You can ask, okay, in this scenario, what is the answer? Most of the time, the answer may be really clear. It's just a mental exercise so that you can just kind of figure out, okay, if this is the scenario, if this is the expression, this is the answer to that expression. All right. So in this case, what would be the answer? In other words, we are focusing on the first one, an empty set union with a set that has 1, 2, 3 in it. 1, 2, 3. Just a set with 1, 2, 3. But since I want to emphasize ordering is not important, let's change the order. Okay? It doesn't matter. What about the next one? A set that has 1, 2, 3 in it, unioned with a set that has 2, 3, 4 in it. 1, 2, 3, 4. Yep, 1, 2, 3, and 4. That is correct. What about this one here? 1, 2, 3. Oh, that's the same. So we'll just kind of change the ordering a little bit because it should not matter. What about the last one?
1, 2 empty set.
Yep. So this one I'm gonna change the ordering a little bit, just to emphasize ordering is not important, right? Just kind of mix things up a little bit. There we go. So we still do okay so far, with the concepts. One is intersection and the other one is union. We're still doing okay? All right, cool. Let's go back to the notes here and find out what is the next one. The next one looks like subtraction. We can call it difference. And this one is kind of interesting because we want if you look at A minus B, I'll just call it A minus B. An element in A minus B is found in A but not in B. Okay, it is quite explicit that it cannot be in B. Okay, but it has to be in A. All right. So now we're going to go through a few examples. Okay, so we're going to go to the examples here. We will look at, okay, let's take a look at an easy one first, and then we'll look at some possibly slightly more challenging ones. So we have with just 2, 3, 4. Okay, there we go. All right, so what is the answer to this expression? What is in the solution, which is a set?
1. 1.
It's going to be 1, exactly, because whatever is the answer to this question, it has to be found in A, but it cannot be found in B. 1 is found in A, but not found in B, so we're good. 2 is found in A, but it's also found in B, so it's no good. 3 is also found in A, but it's also found in B, so that's no good either. 4 doesn't really matter because 4 is not in A to begin with, so it's not even a candidate to begin with. All right, so let me go ahead and type the answer. So it's just 1 by itself. All right. Any questions about the quote-unquote subtraction or difference? Okay, let's move on. So now we move on to a kind of interesting operator. It's called Cartesian product. So Cartesian product is represented by the times symbol, and the end result is a little bit funny. Okay, so when you look at this notation, it's basically saying if you try to find the Cartesian product of A and B, it would become a set. Okay, so the result is a set. But the way the set is constructed is each one is what we call a two-tuple, T-U-P-L-E tuple. You can look at tuple as quote-unquote an array, okay, or a list. So each element is a two-tuple. In other words, it's not just an element. An element has 2 components to it, and ordering is important in this case. You can see how I'm not using curly braces. I'm using just parentheses in this case. The first one in the tuple has to come from A. The second one has to come from B. Is that okay? So this is a rather abstract description of Cartesian product. Now we're going to go through some concrete examples and see if we can actually apply this. And we'll start with something that's simpler, and then we'll gradually move on to something that's more complex. All right, so let's take a look at just this and Cartesian product with that. And what would be the answer? Does anyone want to give it a try? So let's go back to the definition of Cartesian product. The Cartesian product between two sets, A and B, consists of elements. Each element has two components. The first component has to come from A, and the second component has to come from B. So that is how Cartesian product is defined. So now we're trying to apply that to an example where A, the set A, or the first set only has the element of A, and then the set B only has an element of 1. Go ahead. It'll be okay. So can you give me the full description, like including all the punctuations? So it's a set. Okay. So the first thing is we know it is a set. And then the element in the set is a two tuple, which means we need parentheses and a comma in between. The first item has to come from the set to the left-hand side. In this case, we only got one element, which is A. And then the second one has to come from the set on the right-hand side, which we only have one in this case. So are we doing okay so far with this particular example? Okay. We can try out a few other ones, right? So now we'll try to make it a little bit more complex. And we have two elements from the set where we construct Cartesian product out of. So we'll go ahead and say the set on the left-hand side has AB in it, and then the set on the right-hand side has 1, 2 in it. So now the question is, what would be the members of the Cartesian product of these two sets? Yep.
A1 and B2.
All right, so A1, B2 are correct answers, but is that all? Go ahead.
B1 and A2?
B1 and A2. Okay, that is correct. I think that's what you're proposing as well. So that is right. Okay, it actually has 4 elements. It is kind of like a cross product. A2 is an element, and so is B1 as an element. Okay, that's kind of interesting. Let's take a look at another example. So this time we have AB on one set and the empty set on the other side. So now what would be the answer to this question? Whatever is in the Cartesian product, if you pick out a particular element in the Cartesian product, it has to be a two tuple for one thing. The first thing has to come from the left-hand side. The second thing has to come from the right-hand side. But the right-hand side is an empty set, right? What can come from an empty set? No. Well, okay. So if by means of 0 you said nothing, that would be the correct answer. But 0 as a number is not the correct answer. Okay. So if you mean nothing, then the answer would have been right, which means the Cartesian product with an empty set is also an empty set. Are we good so far? Sort of. All right, so one way to visualize this, okay, if you're looking at the Cartesian product, is you can imagine in your head a matrix or table, okay, where the rows are indicating members of one thing, and then the columns are indicating members of the other. I can give you a simple example. Let me think about how to do this. Okay, so I can use a table. You can also use Joplin or Markdown to create tables. So let me see if I can still remember how to do that. I think you have to, so AB, so this time let's work with ABC. and I need something empty here. And then here, you basically indicate what is the separator line, like that. I think I need one more, 4. There we go. And then here we have, let's say 1, and 2. There we go. All right. So you guys can just focus on the right-hand side. So we can now say, okay, what should go here? What goes here is A1, and then what goes here is B1, and then what goes here is C1. And then likewise, on the next row, it's all your A2, B2, oops, and C2. So is that helping you to kind of visualize, how to basically enumerate membership in a Cartesian product? Okay. Well, if you look at it this way, if if one set, the left-hand side, has, let's just say, n elements, and then the other one has m elements, what would be the number of elements in the Cartesian product? It's called a Cartesian product. Yes.
The product of the two.
Yep, exactly. The product of the cardinality of the two sets. Yes. So are we good so far? All right. So it would look like, why would we want to use Cartesian products in a class like this? As it turns out, there are quite a few topics in this class that can actually make use of the concept of Cartesian products. So we'll get back to the Cartesian products in I think in a week or so when we talk about functions. So now we move on. Now we can also define some other set operators that return either true or false. Okay, so if you look at all the set operators that we have talked about so far, they all return another set. Intersections give you another set. Union gives you another set. Minus, subtraction, difference gives you another set. Cartesian product also gives you another set. So now it's time to look at some of the things that you kind of compare to less than or equal to, and also greater than or equal to, also less than and greater than. Okay, so now we look at the first one is a subset of. So we'll take a look at how a subset of is defined. This is a subset of. So in this definition, one thing you might want to, actually I take it back, the actual definition. Well, it is the definition. So A is a subset of B if and only if the difference between A and B is an empty set. That's one way to define it, okay? Not the only way, but one way. All right. Let's try to find out exactly how to understand the expression as it is right now. A is a subset of B if and only if A minus B, which is things that are in A but not in B, there's none of them. Okay. So let's work through a few scenarios. Okay. So you guys can probably, hopefully, remember this definition. Actually, I'll be kind and do this. This is another way to make use of this feature is to copy this, and then you can paste it almost straight up, in Joplin. You do have to include the $sign because that's how Markdown indicates the beginning and the ending of equations. So I'm going to paste it here, and now you have the definition in Joplin, like so, and then we can work out a few examples. So let me ask you, okay, and let's say we have 1, 2 here, and then we have subset EQ. Let's see, 2, 3. All right, so what is the value of this expression? The set of 1, 2 is a subset of the set of 2, 3. What is the answer? False. Very good. Okay. So it is a Boolean result. It's either true or false. Okay. So that is, how did you figure out it was false?
Well, because B doesn't have one, so A minus B is not empty set.
Okay, so you were using the definition. You were using the definition that is right on top of the example. Very good. Okay. And then let's work out another example. And this one, even though it looks tricky, it is actually trivial. So we have this. And we'll just use the same as last time, which is 2, 3. What would be the answer to that question? The empty set is a subset of the set of 2, 3. So you apply the definition, okay? You always want to apply the definition. And what would be the answer based on the definition? In other words, what is A minus B to begin with? It is true because A has nothing, right? So if you're asking the question of what is in A but not in B, the answer is will be nothing because you have nothing to begin with. So that means, A minus B equals to the empty set is true. But because we have an if and only if here, so if one side is true, the other side has to be true. That is how we can determine, the value of the expression. An empty set is a subset of 2, 3 in this case. Well, you guys are pretty good so far. So let's try out yet another example. How about this? Is the empty set a subset of itself? And how do you figure out it is true? So you're going by the definition again. Very good. Okay. So sometimes people think about the term subset, and they have a certain interpretation based on how the term is spelled out. That would not be a good idea most of the time because we can go back to the definitions. So if you go back to the definitions and you just say, what is the empty set minus the empty set? What is in one set but not in the other one? Well, you have nothing to begin with, right? So if you have empty set minus whatever, it's always going to be an empty set, even if the right-hand side of the minus is also another empty set. So that's why we know A minus B is also an empty set, and this equality is true, and as a result, A is a subset of B when A and B are both empty sets is also true. Are we doing okay so far? All right, very good. So now we're going to look at a related definition, which is a subset of. But this is what we call a proper subset. So A is a proper subset of B if and only if A is a subset of B to begin with, and B minus A does not equal to an empty set. So there's an extra requirement, right? Because A is a proper subset of B if and only if, first of all, it has to be a subset of, and on top of that, we also want B minus A to be non-empty. In other words, we want to find at least one thing in B that is not in A. Everything in A has to be in B, but we need to find at least one thing in B that is not in A. All right? So now we're going to go back and look at our examples over here and reapply everything, but this time we are going to use, we ask whether it is a proper subset of instead of just a subset of. So the copy, paste, and modify. All right, so we're going to work with the first one, which is, oh, okay, this one is not right because it's just definition, so we'll get rid of that. All right, so we'll take a look at 1, 2 is a subset of 2, 3, proper subset of. That's an easy one, right? Because it is not a subset of to begin with. If it's not a subset, it cannot be a proper subset of. That kind of makes sense, right? Okay, that's an easy one. What about the second one? The empty set is a proper subset of the set of 2, 3. Well, this time we know that it may be true because the empty set is a subset to begin with of the set of 2, 3. But the question is it a proper subset of? Which means, are there things that we can find in the set of 2, 3 that cannot be found in the empty set? Sure, everything in 2, 3 as a subset, as a set cannot be found in an empty set. So it meets that requirement. What about the last one? A empty set is a proper subset of an empty set. That would be false, because there's nothing in an empty set that can be found in an empty set. Does that make sense? Because an empty set is empty to begin with. There's nothing in an empty set. All right? Are we good so far with all of these notations? Yep.
So a set is a subset of itself, but not a proper subset of itself.
That is correct. Very good. Okay, that is a very good observation. So every set is a subset of itself, but it cannot be a proper subset of itself. Yep.
So isn't the proper subset just checking if the sets are the same?
So
Technically?
proper subset is kind of the same as less than, and then subset of is kind of like less than or equal to.
Yeah, but by definition, isn't it just checking if it's a subset of, but not the same set?
But not the same, correct. You can also say it's not the same.
Yeah, are there any examples of something not being a proper subset and them not being the same set?
Okay, so if you look at this one here, you really kind of have to go to the definition of it has to be a subset of to begin with, and it is not. Do you want to give me a concrete example to evaluate?
No, I think I get it now.
Okay, all right, that's fine. Yeah, anytime you guys want to give me a particular situation, like what about this expression? How do we evaluate this expression? Just go ahead and let me know. Okay, if you don't want to spell it out because it's really hard to spell out expressions like these, just use the whiteboard. Okay, you write it out on the whiteboard, and I can type it in using Joplin, so that way we have a record in the video. Are we good so far? All right. All right, so let's move on. That's it. That's the end of this particular slide, except for the notation of what we see, kind of like the absolute value, is I borrow that notation to also mean the cardinality, which means the number of elements in a particular set. That's just a notation. It's the same thing as if you look at x as a length as a string, this is like string length. Okay, how many things are in a particular set? So it always returns a natural number. Are we good so far? Yes? All right. Okay. So at this point, we move on to talk about the next module, which talks about quantifiers. So we're moving on to basic quantifiers. We're going to take roll later today, but right now we focus on quantifiers. And this is a really, really short module because there's not really a whole lot to say. Okay, there's some, but not a whole lot. So the basic, yeah, go ahead.
Are we gonna go over the
Go over the what? Oh, well, it's not homework. It is just a little
well, yeah, the exercise.
brain teaser. We can call it the brain teaser. Yes, thank you for reminding me, because otherwise I would have completely forgotten about the brain teaser. So you can kind of look at the exams as a bunch of brain teaser questions. Some people do not like that, but All right, so consider the following set definition, blah, 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 blah. Okay, so using this notation, it means in order to become a member of S, this condition has to be met. In fact, this is the if blah, 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 if and only if this entire thing, that something, the value, is a member of S. That's basically what it means. All right, so how do we read this thing? How do we even start with reading this thing here? This is like, well, you do it step by step, just like everything else, step by step, okay? And I would like to remind you guys about, this module that I kept referring to, which is me trying to understand your quantum computing. Quantum computing was completely new to me. So the first time when I saw the symbols, like the this is, I think this is the cat, symbol. I was going like, I have never seen this before. I have very limited exposure to complex numbers also. So everything, everything I had to look up, and it has to stack, all the way down to, and that's why, in the recommendation part, this is how I had to drill down the concept. I start off with quantum computing. I have no idea what that is. Okay, what is qubit? Have no idea. And then it has the cat notation. What is that? Have no idea. So I have to now look down. Okay, what is a complex number? I think I feel comfortable with what a complex number is. I can understand what an imaginary number is. Fine, that's fine. What about complex vector? Okay, I think I got that too. What about space? Sort of. So I have to nest all the way down to the symbols and the concepts that I do understand, and I have to use something like this to track, as I try to understand all the concepts. Because otherwise, I can drill down. By the time I'm over at the meaning of cat 0 and cat 1, I would have forgotten where I started off and how I should back up the tree. So I have to use something like this to keep track of my understanding of the material. But the point that I want to make is it really is just going down one step at a time to try to understand the concepts. Okay, so getting back to the exercise. There we go. All right, so the same thing over here, okay? You look at this and you say, okay, do I understand all the symbols individually? That's the first thing, okay? It's just like when you're trying to read a sentence in whatever language, you need to make sure that you understand every single word/character in order to have a good starting point. It's the same thing here. You have to understand every single symbol. Do I understand what this means? Yeah, it's element of. Do I understand this funny looking z? It's the set of all integers. Okay? But how do I know that? How do you guys know that that funny looking z is the set of all integers? Because it's already discussed in the module, okay? It has been introduced already. So part of this has to do with really just going over the written material and just make note of things that you feel like, oh, I have never seen this symbol before, but the note mentions this is the set of all integers. Make a note of it, okay? Put it into the definition section so that it's easy for you to find the definition of that funny looking symbol. Okay. What about this little TP thing? It's and, okay? How do we know that? It's already introduced, okay? So that's, it's not so much studying, it is knowing where to find your definitions that is important. All right, less than, I think I got that. Mod is the remainder of the division. We talked about that a little bit too. So we're comparing the remainder of x divided by 3, whether it is equaling to 0 or not. Okay, that's all good. And implication. Do we know what implication means as an operator, as a Boolean operator? Yep. And because we know the truth table, okay? The truth table is the definition that you should refer to. So every symbol is now defined. Now we have to look at the parentheses. We have to look at the structure of the expression. So now we say, okay, what exactly is being said here? This is a conjunction. On one side, it's easy. On the left-hand side of the conjunction, all it's saying is x has to be an integer. Okay, that's not too hard. What about on the left-hand side? The left-hand side, the right-hand side is a little bit more complex because now we're using a implication operator. It says x is less than 0 implies x mod 3 equals to 0. First of all, x mod 3 equals to 0 is the same thing as saying x is a multiple of 3. So that's an easier or more intuitive way of looking at that expression. Okay, if that helps you, use the more intuitive interpretation. But I'm still having a problem here. if x is less than 0, then x mod 3 has to be 0 in order to make this entire thing true. So that means if x is, okay, we'll go through a few examples. What if x equals to 1? If x equals to 1, is the implication true or false? I'll let you guys answer that question. If x equals to 1, is the implication as an operator true or false? How would you evaluate that? Truth table, right? But in order to work out which row of the truth table to look up, you have to say, okay, what is on the left-hand side of the operator? 1 is less than 0 is
False.
false. What about on the other side? 1 mod 3 equals to 0 is also false. So when you look up the truth table, you have to look up the row where both independent variables are false. The truth table in that case will tell you, oh, in that case, the operator itself will return the value of true. So even if you're having some struggles of, okay, wait, hold on a second here. In normal conversation, if I use the word if, that is not how I understand it. It doesn't matter, because if the truth table says it is the case, it is the case. So that is one good thing about just referring back to the truth table definition, is you don't have to worry about the ambiguity because how we normally use certain words. Will be good? So 1, if x equals to 1, this entire thing is true, which also means 1 is a member of S, right? So that kind of goes for 2 too, right? Because the only difference between 1 and 2 is 2 is a little bit bigger, but it meets both requirements too, in the sense that 2 is an integer, 2 is less than 0 is false, and you know what? If the left-hand side of an implication is false, I don't even want to bother to look at the right-hand side. Because if you look at the truth table of implication, both rows having the left-hand side being false would end up with a final value of true anyway. So the right-hand side value doesn't even matter if the left-hand side is known to be false to begin with. So you can just kind of shortcut the whole thing and go like, hey, oh, wait, hold on a second here. So that means anything that can make x is less than 0 false would automatically make the implication true. So that means if x equals to 0, the whole thing is going to be true. The implication is going to be true. Anything, any integer that is non-negative is going to be in the set S as a result. Is that okay? So now the only thing you have to work out is, okay, fine, but what if x is less than 0 is actually true? Well, in that case, you do have to evaluate the right-hand side. So we'll go with, what about -1? Okay, consider x being -1. Is -1 a member of S? It is not. Why not? Well, -1 is less than 0 is true. -1 mod 3 equals to 0 is false. So if you look at the truth table, where the left-hand side is true, the right-hand side is false, then implication is false. All right? So that goes for -2 as well, but with -3, it is true on both sides. And if both sides of implication is true, then the implication itself is also true. So -3 is an element of S, -4 is not, -5 is not, -6 is, and so on. So the set S would actually consist of negative multiples of 3 and all the non-negative integers. Are we good so far? So this is an exercise because I want you to basically make sure that you understand all the symbols on their own individually, and also be able to interpret something that is structured, even though this particular set S probably has no particular usefulness. It is just an exercise, okay, to basically make sure that we understand how to apply the operators. Okay, so that means 3 is an element of S, it's good. 4 is an element of S is also true. -3 is an element of S is true. -4 as an element of S is false. Oh, that cannot be true, right? Because each member of the set S has to be a number, and it cannot be another set, okay, based on how it is defined. I mean, think about it. how do you compare? Okay, first of all, is the set 3, 6 an integer? Nope. Okay, it failed the first test already. It cannot be a member. What about this one here? Hmm? Is it true or false?
Logical.
It is true, because 3 is an element of S, is true. 6 is an element of S, is also true. True and true is true.
It's logical, I need integer.
Logically?
No,
You're saying from, because like the previous one, you needed
all
an integer.
logical,
Right.
true, I need integer.
Right.
To false. Then false.
Using the logic that we use to determine membership of S, we can determine that 3 is a member, 6 is also a member, and then true and true is true. Right? That's how I would work on it, is to step by step determine the membership first, and then determine what is the conjunction, or the value of the conjunction. Go ahead.
Why is 4 true then?
Why is 4 a member of S?
Yeah.
Because 4 is less than 0 is false. Okay, let's start from the beginning. Is 4 a member of the set of all integers?
Yes.
Yes, okay. So now we have a conjunction. And on the right-hand side of the conjunction, we are asking, first of all, is 4 less than 0? The answer is false. But this is the left-hand side of an implication. If the left-hand side of an implication is false, the implication itself is true.
And what about negative 4? You said that's true.
For negative 4, the answer is false. So negative 4 is not a member of S.
I thought you said it's true, so I got confused.
I could have misspoken, but it's all getting recorded, so we can check that. Yep, go ahead. Oh, I thought you had a question? Nope. Okay. All right, it's 4 o'clock. Let me take roll. Yes.
Last element is logical.
What is logical?
No, this logical, all element. This logical.
It gives you a Boolean. That is correct.
This Boolean.
Yes.
Boolean.
Each.
I need integer.
So 3 is an element of S, will give you a Boolean answer. Is either true or false?
No matter logical. Is this logical?
Okay, so when you said, is it logical? Are you asking, is it a Boolean type? Or are you
Boolean type.
asking whether it is logically true? Because those are two different ways of interpreting what you just said. Yes, go ahead.
I think when you use like 3 is an element of S, is not an integer, so how are you evaluating it in that? Because the rest, like 3 is like the top one, you can plug it in for X, but how can you plug in 3 is an element of S into X?
Okay, so first of all, what is S? It is a,
X and
it's a set, okay? So if S is a set, I can always ask this question of, hey, is this thing in the set? I can always ask, right? The answer is either, yes, it is in the set, or it is not in the set. So in this case, it is really asking, S is a set already, I want to see if 3 is a member of S. And there are only 2 possible answers, true or false. So from that perspective, what you said, that 3 is a member of S is logical, is correct from the type perspective. It is a Boolean result. It's either true or false. Because some people equate Boolean type as quote unquote logical. I think that's why we call and as a logical operator. It's a Boolean operator. So Boolean and logical can refer to the same thing from the type perspective. But the other way to interpret your question is it logical for 3 to be a member of S? That's the other interpretation of what you said of is it logical? So that's why I have to differentiate which one did you mean, because if you were asking 3 is logically a member of S, then it can only be coming from 3 is greater than or equal to 0. As a result, the implication is true. Then we end up with true, and as a result, 3 makes this condition true, and as a result, 3 is a member of the set. I know what I said seems to be confusing, but that's what that's one of my superpowers. Is if there's a way to misinterpret something, I will find it. It's not a very useful superpower, but nonetheless it is. My other superpower is I know when I don't understand something. If you think about it, it's not a very useful superpower, or at least it does not seem to be a super useful superpower, but it is, okay? Because if you're a student learning something and you can actually tell whether you're really understanding a concept or not, it's really useful because at least you know, okay, maybe I need to study more, or I need to ask the professor, or I need to look up something, as opposed to a false positive of saying, yeah, I think I got it, but you're not actually getting it. That would be bad because later on, down the line, you might find out that, okay, this is not making sense because an earlier concept did not make sense already. All right. So is that answering all the questions regarding the brain teaser? I think so. All right. Cool. So now we can take roll. So the way I take roll in the class, because I forgot to take roll on both class meetings last week, is I just give you an activity where the answer is shown to you on the projector. I am just going to reuse this particular activity and change the answer potentially. So I will show you the answer right away, and then when I release it, you just have to type it. So the word is union, all lowercase. I'm going to write it on the whiteboard, so this way you won't forget. So union is the correct answer. And then what I do is I just give you a deadline to do it. So you need to have access to Canvas at this point, or before the deadline. I can see some people are not using a computer, so I'm going to give you guys up to 5 o'clock. Would that work? Because the class ends at 4:20, so you just have to find a computer or use a cell phone to sign into Canvas and answer the question. Would that be okay? Okay. So I'm just going to say 5 p.m. 5 p.m. Save and publish. So now I forgot to change the name of the activity. So I'm just going to say this is 0829, which is today's date. So now you can find out where you can find the activity and just say union. All right, so let me show you where you can find it. So I'm going to pretend that I'm a student, turning on student view. So this is what you should be seeing or close to what you're seeing. So you basically you just go to set theory, find row taking activity, go there, and say you take the quiz, and the answer is union. Submit quiz. That's it. That proves that you are here. All right? So if you don't have a computer in front of you, just kind of write down the answer. And after class, I would do it as soon as possible before you forget. Go find the computer in room 301, the main lab. We have rows and rows of computers and hardly anyone using those computers. So go there and log into Canvas, type in the answer, and you'll be considered as present. All right, so that's clerically how I take role in this class. And now we can move on. We can move on to quantifiers. All right, so let's go ahead and look at basic quantifiers. All right, so quantifiers, okay, so we'll go ahead and begin with this notation. What exactly does that mean, okay? First of all, what is the type? Because we always want to know what is the type of the result of evaluating an expression. So to say this in English, it means for all x, p of x is true. That's basically how you spell it out. That's how you pronounce it, as a sentence. So what do you think is the type returned by the expression?
Boolean?
It's a Boolean, very good. So it is true that for all x, P of x is true, or it is false, okay? That for all x, P of x is true. Is there an easier way to say this? Okay, can we not use like special terms in math and just say words that we use in normal conversation? P of x is true for every x.
Like and for the set?
Hmm?
It's like using an and operator for every element in the set, kind of?
Yep. Well, not exactly. Okay, so I'm gonna show you why it is not exactly the case. Okay, what you said is almost true, except for the extreme case of what if the set is empty. So when you say every, okay, so let's just say that we have an empty room. Okay, nobody is in a particular room, and I say everybody in that room sucks. Would that be true or false? But there's no one in the room. Can I still say everyone in that room is a good student?
You can,
Yes.
but it's not logical.
Okay, so I'll give you the pseudocode to evaluate that situation in just a little bit. But right now we just say, oh, that is just every, okay? In other words, when you use the word every, all, always, those are all universal quantifiers. And this one here is what we call an existential quantifier. This is a universal, this is existential. Existential quantifier is when we use some, at least one, it becomes an existential quantifier. So the way we pronounce this one is for all x, P of x is true. And the way we say this one is there exists x such that P of x is true. Are we okay so far? So let's just say that, so P of x, what exactly is P of x? Well, we talked about P of x already. P of x is a predicate. In other words, it is a Boolean function. It's a function that returns a Boolean value. And you're just, it has one single parameter in this case. So it's really just evaluating a Boolean expression for whatever value x you want it to evaluate. Are we doing okay so far with the universal quantifiers? All right. So now we want to look at the negation of something. In other words, what about the negation of the existential quantifier, so that we are basically saying it is not the case that there is at least one x such that P of x is true? What is the other way to say that? If you scroll down a little bit, you'll find the answer. But let's just kind of think about this for a little bit. It is not the case, because this negation applies to the entire thing. It is not the case such that there exists x such that P of x is true. What is it really saying? What is the easier way to say the same thing? Yep.
Always false.
Not always false. Yep.
No x makes P of x true.
It is not the case. Yep, okay, never mind. I take it back. You're correct. So for every x, P of x is false. Is that kind of what you're about to say? Yep. So this is the same thing as for every x you can find, P of x is false. Does that make sense? Okay, so intuitively it makes sense. So that means this expression here is the same thing as this expression here. You can move, quote unquote, you can move the negation from being applied to the quantifier so that it applies to the predicate. But by doing so, you have to change the existential quantifier from an existential quantifier to a universal quantifier. Are we good so far? All right. What about this one here? It looks, kind of like the opposite of what we were talking about. So this one, if you want to spell it out, if you want to read it as a sentence, it is saying it is not the case that for every x, P of x is true. So if I want to move the negation to the predicate, what is it going to spell like? Or what is it going to sound like? It is not the case that for every x, p of x is true. So how can I, okay, another way to look at this is how do we convert it into an existential quantifier? Go ahead.
You say there is an X that makes P of Q false.
Exactly, very good. So the answer to this question is, it is the same thing as saying there exists an X such that P of X is false. Okay? There we go. So they mean exactly the same thing. But so far, we haven't really talked about, when we say for all x, what are we talking about? Okay, for all x, p of x is true, or for all x, p of x is false. What do you mean by for all x? What does that mean? Are we talking about numbers? Are we talking about names? Are we talking about addresses or coordinates or people? What do you think? What do you think is the answer to that question? Yep.
Value.
It's not just values. When we use for all, we are talking about everything that exists now, in the past, and possibly in the future. It is universal, as in really, really universal. And you guys will be asking, but why do we care? I mean, this class is all about discrete structure. It's about counting. So numerical value, I can see how it is important. But why would what kind of car tech is driving and be important in questions like this? Well, it's not. Okay. So when you look at the quantifiers, they actually include everything. And I should not say everything under the sun, because it also includes everything that is not under the sun as well. So it's including everything, okay? A lot of stuff that you really do not care about. So the notation is so when we want to filter and say, for the most part, we only care about, when um, the universal quantifier is applied to integers, okay? Then you use this notation to say, if E is not an element of X, I don't even care. That is what this notation is saying. But it is using the implication operator. So what is the effect of this implication operator? Let's just say that X, the set X here, is a set containing the elements where we really care about, okay? Integers, for instance, okay? And then there are also a lot of stuff that we don't care about, like irrational numbers, complex numbers, and stuff like that we don't really care about. So what is this going to do? If I say X is the set of all integers, okay, meaning that I want to filter everything so that only integers matter, okay? What if E is a complex number? What would happen to this expression? A complex number is a member of the set of all integers. Is that true or false?
False.
It will be false. But since this is an implication, what would be the value of the implication itself? True, right? So that means for everything that is not in the set containing things that we're interested in, the implication is automatically true. So now, what can make this entire thing false? Things that are in the set X, but it makes P of E false. Those are the only things, those can be the only reasons to make this this universally quantified statement false. So by doing this, we now say, there are a lot of things in this universe. Most do not matter for what I'm talking about. I can now say filter, okay? Just pay attention to only those things that we want to work with. And everything else, we can now say, quote unquote, they don't matter anymore. Because they cannot make the universally quantified statement false. So they don't really matter. Is that making any sense? Okay, the idea is basically to filter. And if you want to filter in in an existential quantifier, this is how you do the filter. So if X is representing everything that we care about, we only want to work with those values, this is how you filter out, everything else. Because when you're working with the existential quantifier, then you want to say, would anything outside of the set that we're interested here accidentally make this entire thing true? That would be bad. Okay, because you want to be able to make this entire quantified statement true only working with elements inside X. Everything else should make it false. So by doing it like this, so once again, if X is the set of all integers, implying that we're only interested in working with integers. And then E turns out to be a complex number. A complex number is an element of the set of all integers. It's false. But this time, instead of an implication, we have a conjunction, which means if one side is false, the whole thing has to be false. So that means anything other than integers will automatically make this part of the statement false. We cannot accidentally have a complex number to accidentally make the existentially quantified statement true, which would be bad. Is that okay? Let me give you an analogy. We are running out of time, but I think this analogy will help. Okay, so universally quantified means every, right? So you can say, is everyone a good teacher? Okay, well, but that will apply to the janitor, that will apply to the administrative assistant, it will apply to the administrators and so on, which really doesn't really apply because they are not in a classroom, they're not teaching at all. So you want to be able to filter out and say, okay, maybe we should just focus on professors. So the way you filter out everyone else, people who do not teach, is to use implication. So the outer part will still be asking, okay, is everybody blah, 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 okay? But that blah, blah, blah is now saying E is a professor, implies E is a good professor, is a good teacher, can teach well. So now you're basically focusing on just can all the professors teach well? Instead of saying, is everybody teaching well? Because you don't care, if that person is not a professor, whether they can teach well or not, because it's not their job. So when E is an administrator is an element of the set of all professors, it's false. So that makes the implication true automatically. So that means, it cannot make the universally quantified statement false accidentally. So just having a few administrators who cannot teach in the classroom doesn't affect the statement of are all professors good teachers. Is that making any sense? I'm just trying to give you some concrete examples so that you can understand the mechanism of filtering. Well, we're out of time, so that means, for you guys, if you have time, and I think you should make time if you don't, finish up this entire module. And when you're done with this module, next time when we come back, I think we'll have time to go back to set notations. But this time we'll utilize quantifiers for explaining the same thing in basic set theory, but this time we'll be making use of quantifiers. And quantifiers are going to be useful throughout this entire semester, just like all the set notations. And that's why they're super important. In other words, right now, we are introducing the lexicon of how to express algorithms and other things, and we're going to be using it for the entire semester. All right, so we are done with today's class. I'll see you guys on Wednesday. But I'm going to stay behind because I have a meeting with the dean, and instead of moving to some other place to turn on my computer, I'm just going to stay here.
So for the roll call attendance, I know we have to go through Canvas.
Yep.
I did enroll in the class, but I'm just waiting on Canvas for it to load up because it still takes a while.
All right, so what's your name?
Pedro Ventura.
Oh, okay.
Yeah.
Right.
So
Okay.
that's what you said. I
All
was
right.
reloading it to see maybe if it popped
Okay,
up.
gotcha.
Yeah.
Let me do this. Let me turn off the projector first. All right, so I can just hand enter your presence here. Oh, I'm still in student view. There we go. And your last name is?
Ventura with the B, E-N-T-R-A.
That's your last name?
Yeah.
I don't see you here. You use the permission number?
Yeah, it says I'm enrolled
You
on
said-
the
okay,
e-service, but then on Canvas it's not loading yet.
Huh, that
Yeah,
is
I
weird.
have it yeah.
It can work, sometimes it happens the other way around, but this
Oh,
is the
okay.
first time I see it like this. Well, in that case, I can't really take roll for you. Because, even if I wanted to, because you're
Yeah.
not in the class. Okay, hold on a second. Let me see if I can just, manually add you as a wait list.
Okay.
So this will give the system some time to sink in. All right, so let me do it this way. What is your student ID? This I do need, because otherwise I can't really. Okay.
Okay, so it's 204
204
4698.
4698. Okay. And I'm going to add you as a wait list. It doesn't make any difference. You can participate in all the activities, just
Okay,
like a
sounds good.
student. So let me see, next. All right, so that's you. Add users. Okay, there we go. So now I think I can take row for you. This one. Pedro, what was the last name again?
Ventura?
V, okay.
Yeah.
Okay.
Oh.
I mistook it as B.
Oh,
Okay.
okay.
So I misheard. Sorry. That was my. There we go. So
Okay,
you're good.
thank you.
Mhm.
Appreciate it.
Yep.
If you have time, I was wondering if you could explain to me the quantifier, like why it's not and for everything. Like the Boolean logic.
I have a meeting starting at 4:30, so I can't do it
Okay.
today.
Can I come in before on Wednesday?
Yeah, absolutely.
All right, cool.
Yeah, so on Wednesday you can come in because you're in my 310 class too, right? Yeah, so you can come in. You can find me anytime before 10:30.
Okay, cool.
Mhm.
Thank you.
Mhm. Yes, sir.
I do solution at home. Yeah, I think maybe X will be element this
Substituting value into
this
X.
what I write element no every element 3
Yep.
4 minus 3
Yep. Yep.
this is this
That is not an element.
this
Because I want you to because this is an expression.
this
Right. Yep.
okay
Yep.
okay
Okay.
okay
So now I'm starting to see
Okay,
why
okay.
you asked the question.
okay mistake
That's okay. Not a problem.
okay
Yep.
Need this
Right. Yep. Because this.
this
Yep.
yes okay
Yep.
okay
Yep. No worries. Yeah. That's fine. Alrighty.
First, I